Good day, viewers. Welcome again to this channel. Thank you for always coming to this channel to view and to learn from this channel. And as you watch this channel, I want to plead that please help to subscribe. And as you do that, the Lord will bless you. Uh, as we proceed in our series of lessons, today we'll be moving on to another aspect and very important. And that aspect is what we refer to as electrolysis. Electrolysis. That is the aspect we want to look at now. And when you look at this topic, is an aspect of chemistry that so many students are afraid of. Not only students, so many tutors, they are always dodging these aspects as a result of limited knowledge. But I want to go through this series. And as you follow on, I want to believe that we shall understand the concept altogether. Now, talking about electrolysis, what do we mean? Electrolysis is the decomposition of a chemical substance when an electric current is passed through either a solution of the compound or the molten compound. The decomposition of a chemical substance when an electric current is passed through either a solution of the compound or the molten compound. What do we mean? In this electrolysis, we are actually accomplishing a type of reaction which is referred to as decomposition reaction. And there are different ways decomposition can be carried out. We have thermal decomposition, we have heat decomposition, we have catalytic decomposition, and we have electric current decomposition. And that's what we are achieving under this concept. So when there is a decomposition reaction of a chemical substance, by allowing electric current to pass through it, what that is doing is electrolysis. And as we look at this concept, we shall view all substances in two. One, we look at conductors. All chemical substances, we try to categorize them into conductors and non-conductors. Now, when you talk about a conductor, what do we mean? A conductor is any substance that allows electric current to pass through. Any substance that allows electric currents to pass through. And of course, you could have examples to be electrolytes. Example could be metals. Any metal at all, they are all conductors. And on the other hand, a non-conductor. A non-conductor is a substance that does not allow electric current to pass through. A non-conductor is a substance that does not allow electric current to pass through. Any substance that does not allow an electric current to pass through it is referred to as a non-conductor. And we could refer to a stick as being a non-conductor. We could refer to a stone as being a non-conductor. We can refer to any substance that cannot allow current to pass through as conductor. Now, there are other terms we're going to look at under this topic. We're going to look at electrolyte. Electrolyte. When we talk about an electrolyte, what do we mean? An electrolyte is a compound which either in solution or in molten form allows electric currents and is decomposed at the electrode in the process. An electrolyte is a compound which either in solution form or in a molten form allows electric current to pass through and is decomposed at the electrode in the process. Any substance, any compound that allow current to pass through, that means that substance is a conductor. And beyond being a conductor, it now decomposes. That is, it breaks down. It splits into its ions during the process. That kind of a compound is referred to as an electrolyte. And we have example to include acids, alkalis, and salts. Talk about an acid. All acids are electrolytes. All acids are electrolytes. We're talking about an acid. You can refer to an HCl as an acid. It's an electrolyte that allows electric current to pass through and eventually it will decompose into its ions at the electrode in the process. So any compound or substance that allow current to pass through and decomposes at the electrode in the process is referred to as an electrolyte. Also, all alkalis are also referred to as electrolytes. Alkali like sodium hydroxide, is equally an electrolyte. When it decomposes, it breaks into its ions. In solution form, it breaks into its ions, Na plus and OH minus. So it's a compound and it's an electrolyte. Apart from that, we talk about salts. A salt is also an electrolyte. A salt allows current to pass through and is decomposed at the electrode in the process. Now, you need to understand and get something straight here that referring to a salt as referring to a salt as an electrolyte, that means that it is not all salts that could be called electrolyte. What I mean is this: a salt can only be called an electrolyte if it's in its solution form or in its molten form. That is, when you have dissolved it in a solvent, then it becomes an electrolyte. If that substance, if that salt is still in its solid state, there is no way it will conduct an electric current. There is no way it will conduct current. There's no way it will allow current to pass through. So salts can only conduct current when they are in their solution form, in their aqueous form, that solution form, or in their molten form. That's when a salt can conduct current. Take for example, if you have sodium chloride. Sodium chloride is common salt that we use at home. Sodium chloride in a solid form, it remains together. The ions are glued together. So when you allow current to pass through it, nothing will happen. It will not conduct any current. But when you now talk about the same sodium chloride in a solution form, in its aqueous form, in that case, it will separate into its ions, Na plus and Cl minus. Na plus and Cl minus. The ions are separated from each other, and for that reason, it will allow electric current to pass through. So a salt can only be called an electrolyte if it's in solution form or in molten form. Now, we also look at this electrolyte. Electrolyte can be classified into two. We have strong electrolytes. We have weak electrolytes. A strong electrolyte is an electrolyte that is ionizing completely in solution. Strong electrolyte is an electrolyte that ionizes completely in solution. The examples we have given above of an acid, of a base, or of a salt, they are all strong electrolytes. And we could also have a weak electrolyte. A weak electrolyte. A weak electrolyte is an electrolyte that partially ionize. They partially ionize in solution. An example of it is water. Water is a weak electrolyte. Now we move on to another term. We consider non-electrolytes. Non-electrolytes. What are non-electrolytes? A non-electrolyte is a compound which either in solution or in molten form does not allow electric current to pass through and is not decomposed at the electrode. A non-electrolyte is a substance which either in solution or in its molten form does not allow electric current to pass through and is not decomposed at the electrode. That is a non-electrolyte. And we have an example of that in sugar solution. Sugar solution, no matter how much you pass current into it, it will never conduct current. Current will never flow through because it is a non-electrolyte. It will never decompose at the electrode. and perhaps because it's an organic substance, an organic substance. Also, alcohol is a non-electrolyte. Toluene is another organic solvent, is a non-electrolyte. Benzene, another organic solvent, is a non-electrolyte. Tetrachloromethane is another organic solvent, is a non-electrolyte. Ether is another organic solvent, is a non-electrolyte. All these are examples of non-electrolytes. They do not allow electric current to pass through them, and they don't decompose at the electrode in the process. Now, we shall look at another term, which is electrodes. Electrodes. What is an electrode? An electrode is usually a conductor. Usually a conductor. And mostly they are metals. Metals like platinum, they are conductors or they are electrodes. Metals like copper, they are electrodes. Metals like mercury, they are electrodes. Metals are usually used as electrodes. However, we have a non-metal that is equally used as an electrode. A non-metal, even though non-metal they don't conduct current, but this non-metal is used as an electrode, meaning that it can conduct current, and that non-metal is referred to as graphite. Graphite allows current to pass through it, so it's a conductor. Why is graphite a conductor? It's a conductor because it has free mobile free mobile electrons, like the other metals. All the metals, they have free mobile electrons that is making them to be very active. The same way, this graphite has free mobile electron. That is the reason why it's conducting current, and for that reason, it's used as an electrode. The electrode, they are usually medium through which electric current enter or leaves the electrolytes. They are medium through which electric current enter or leaves the electrolytes. And these electrodes are classified into two. Electrodes are classified into two. We have the anode. And number two, we have the cathode. Anode and cathode. They are the examples of electrodes. Now, when we talk about the anode, the anode, the anode is the electrode that carries electric current from the power source. It carries electric current from the power source to the electrolyte. It carries electric current from the power source to the electrolyte. And we can refer to it as a positive electrode. A positive electrode. Now, let's view this diagram. In this diagram, we will see that the anode, this is a typical electrolytic cell. A typical electrolytic cell. This electrolytic cell, you can see the anode. This is the anode. You can see the cathode. This is the cathode. And we have the electrolyte. Again, we have the power source. Here is the power source. The power source. And the current flows from the power source and flows through the anode into the electrolyte. It flows from the power source through the anode into the electrolyte. Now, as the current enters into the electrolyte, it decomposes the electrolytes. And again, the current moves out through the other electrode, the anode or the cathode, move through the cathode and out of the cathode, back into the power source. The anode, like I said, is the one that brings in electric current into the electrolytes. And the same anode also carries electrons. It carries electrons out of the electrolytic cell into the electrolytes, into the power source. The current enters through the anode, an electron goes out through the same anode. Current enters through the anode, an electron also goes out through the anode. That is about the anode. And at this anode, there is a specific reaction that occurs at the anode. And that reaction is an oxidation reaction. Oxidation occurs at the anode. And when you talk about oxidation, oxidation is loss of electron. Oxidation is loss of electron. That means at this anode, there will be a loss of electron during the process of an electrolytic process. Electron will be lost. And once the electron is lost at this anode, the electron flows out through the same anode into the power cell, into the power source. So that's why I said the anode carries electron out of the electrolytic cell and also brings in current into the electrolytic cell, right into the electrolyte. Now, the other type of the electrode is the cathode. The cathode is the negative electrode. You can see the cathode being the negative electrode. The cathode, as a negative electrode, it takes electric current out. It takes electric current out of this cell back into the power source. It takes electric current out of this electrolytic cell back to the power source. As it does that, it also brings in electron. You know, I told you earlier that electron goes out through the anode. When the anode loses electron, leaves the electrolyte through that same anode to the power cell, to the power source, and then comes in through the cathode. So the cathode brings in the electron, and the same cathode takes out the electric current back to the power source. And at this cathode, there's a specific reaction that occurs at the cathode. And that reaction that occurs at the cathode is referred to as reduction. And when you refer to reduction, reduction is gain of electron. Reduction is gain of electron. That is a reduction, a gain of electron. Meaning that whatever comes into the cathode, we gain an electron. We gain an electron. Reduction is gain of electron. So as the ions get to the cathode, they gain electron. We still look at some other things attached to this process as we go on in our lesson. Now, the next thing we'll be looking at is ionic theory. Ionic theory. We shall consider ionic theory. An ionic theory. Now, when you talk about ionic theory, a theory is an unproven hypothesis. There is still a doubt about the theory. You call something a theory, that means it is subject to change. It can still be changed. It has not been established completely. That if anything comes up, it can still be changed. We call it theory. Now we are looking at ionic theory. That is the theory that is governing the movement of ion. And this ionic theory was put up by a man called Ionius. Ionius was a man that put up this theory. And the theory states that when an electron is melted or dissolved in water, the substance breaks up. When an electrolyte is melted or dissolved in water, the substance breaks up. That is, it dissociates into freely moving charged particles called ions. The theory states that when an electrolyte is melted or dissolved in water, the substance breaks up or dissociates into freely moving charged particles called ions. That is the theory. Now, the process of dissociation here is known as ionization. The process of dissociation is known as ionization. that the process of the splitting of a compound into its ions is known as ionization. The aqueous solvent, which is water at this point in time, also dissociates. And when water dissociates, it dissociates into water H plus and OH minus. H plus and OH minus. So the ions move randomly during electrolysis as electric current is passed into the electrolyte. So the ions, they move randomly during electrolytic process as the electric current is passed into the electrolyte. Now, by this movement, the positive ions, they move to the cathode, while the negative ion, they move to the anode. The positive ions, they migrate to the cathode. When you talk about the positive ion here, the positive ions are referred to as cations. Back to this diagram, the positive ions are referred to as cations. So positive ions, cations, they move to the cathode. Here is the electrolytic cell. Now we have the cathode. As the current moves from the power source, as the current moves from the power source, as you can see the power source here, as the current moves from the power source, it flows through the anode into the electrolytic cell. And inside the electrolytic cell, the electrolyte decomposes, ionizes, dissociates into freely moving ions. And after the ionization, then the positive ions migrate to the cathode. All the positive ions in solution, they all migrate to the cathode, where they will undergo their respective reaction. Already I told you that at the cathode, the type of reaction that occurs at the cathode is reduction. So as the positive ion get there, either of them will undergo reduction. On the other hand, the negative ions, they will all migrate. The negative ions, they are referred to as the anode. They will all migrate to the anode. Negative ions, anions, they will all migrate to the anode. And as it gets to the anode, remember the anode is the positive electrode. So negative ions migrate to the positive electrode. Positive ions migrate to the negative electrode. So the cathode is the negative electrode, while the anode is the positive electrode. So the negative ions, they will migrate to the anode, which is the positive electrode. And as they get to the anode, they will undergo the reaction that is supposed to be undergone there, and that reaction is oxidation. So meaning that of the set of ions that comes to the anode, either of them will undergo oxidation, which is a loss of electron, Now, proceeding from this moment, when the ions now get to their respective electrode, at every point in time, pairs of ions will get to a respective electrode. Pairs of ions will get to the respective electrode. Now, as it gets to the respective electrode, what exactly happens there? That is where what we are looking at now will now happen. There will be some factors that will play out that will determine of the pair of ions that gets to the respective electrode, which of them will undergo the particular reaction we have mentioned relating to a particular electrode. And we have three factors that govern the selective discharge or the preferential discharge of ions. There are three factors. Number one factor is the position of the ion. Position of the ions. Position of the ions in the electrochemical series. The position of the ions in the electrochemical series. Remember, we are dealing with ions here. So we're talking about position of the ions in the electrochemical series. Now, as we look at the position of the ions, that's the first part. Then number two, we have the concentration. The concentration of the ions in solution. The concentration of the ions in solution and or in the electrolytes. And number three, we look at number three, which is the nature of the electrode, the nature of the electrode that is used, the nature of the electrode that is used. Now we pick them one after the other. As we look at them, we pick them one after the other as we look at the factors, how they affect the selective discharge of ions. The first there that we'll be looking at is the position of the ion in the electrochemical series. The position of the ion in the electrochemical series. There is a list of ions which we refer to as electrochemical series. Now, as you consider the ions on the list, we have potassium being the first on the list of all the cations. Potassium is the first on the list. After potassium, we have sodium. After sodium, we have calcium. After calcium, we have magnesium, aluminum, zinc, iron, tin, lead, hydrogen ion, copper ion, mercury ion, we have silver ion, gold ion, lead-2 ion, gold ion rather, then platinum ion. These are the cations, the list of the cations according to the activity series. This is what we refer to as activity series. So potassium being the first, sodium being the next, calcium, magnesium, aluminum, zinc, iron. We have iron, tin, and then we have lead before coming to hydrogen. That is for the cations. And for the anions, we have F minus, that's fluoride ion. We have tetrasulfate ion. We have triazole 5 ion. We have chloride ion. We have bromide ion. We have iodide ion. And we have finally the hydroxide ion. We have again fluoride ion, tetrasulfate ion. We have triazole 5 ion, NO3 minus, chloride ion, bromide ion, iodide ion, and hydroxide ion. This is the order of preference in which the ions are discharged. In actual fact, you need to understand that the position in which an ion appears determines if the ion will be discharged or not. A lower ion will always be discharged in preference to its higher one in the activity series. A lower ion will always be discharged in preference to the higher one. Let's take for example, if sodium, for instance, sodium ion should come in contact with hydrogen ion in an electrode, I mean at the cathode, the two of them should meet each other at the electrode. When you look at the two of them, hydrogen is very low in the series, while sodium is the second in that list, very high up. So it is the lower one, which is hydrogen, that will be discharged, giving preference to sodium ion. By being discharged there, it means that it is hydrogen ion that will undergo the respective reaction, the reaction at the cathode, which is the reduction that we're talking about. So the lower ion that is being discharged is the one that will undergo the reaction, which is a reduction reaction at the cathode. Now, let's also look at the anion side. If chloride ion, for instance, should come in contact with an hydroxide ion, the two of them meeting together at the same electrode, which is the anode, the two of them, which one will be discharged? It is OH minus that will be discharged because it's lower than chloride ion. So it is the lower ion that will be discharged, giving preference to the higher ion during electrolytic cell. Meaning that when the current flows through the electrolyte into the electrolyte will decompose. Once it decomposes, The positive ions migrate, according to ionic theory, to the cathode, while the negative ions, according to ionic theory, migrate to the anode. And as they get there, the lower of the two ions migrating now, the lower ion there is the one that will be discharged at the particular electrode. That is what we mean by the position of the ion in the electrochemical series. So it's the lower ion that will be discharged, giving preference to the higher ion. Again, the second factor is concentration. How does how does concentration of the ions, how does it affect concentration of the ion? How does it affect the discharge of ions? How does it affect the discharge of ions? Now, at a point in time when the order of discharge of ions can be reversed, is a point in which we have one of the ions having a higher concentration, or one of the ions coming to the electrode having a higher concentration. And this often affects the anode side. It affects the concentration effect, has effect on the anode side. Basically, the ions that come to the cathode side, they are usually metals. And metals, the concentration may not be obvious, as you see in the non-metallic ions. So basically, the concentration of the ions has the effect. The effect is very loud and prominent at the anode, at the anion side. Now, if two substances, two ions, if they meet themselves at the anode, and one of the ions coming to the anode is of a higher concentration, obviously, the position of the ions that should have been the way the order of discharge will be jettisoned, will not be reckoned with, because one of the ions now is having an higher concentration. So regardless of the position of the lower ion or the higher ion, it is the ion with the higher concentration that will now be discharged. Let's take, for example, if you have an electrolyte, maybe you are given concentrated sodium chloride solution. You are given concentrated sodium chloride solution. If you are given this solution, and when it ionizes, it gives you sodium ion and chloride ion. Remember you were told that it's concentrated sodium chloride. Once it's concentrated sodium chloride, that means the chloride aspect of it, half of it, is highly concentrated. So when the chloride now with the hydroxide, if they now meet themselves at the anode, the chloride and the hydroxide ion, if they meet themselves at the anode, bearing in mind that chloride is having a higher concentration than the hydroxide, under normal condition, it is OH minus hydroxide ion that should be discharged at the anode. But because the chloride is now having an higher concentration as stipulated in the question, then the chloride will be the one to be discharged instead of the OH minus being discharged. But that does not have effect on the cation side. The concentration effect does not have effect on the cation side. It only has effect on the anion side. That is how the concentration of an ion can affect the discharge of ion. However, if two ions are so widely separated in their positions, the effect of concentration is also minimal. If two ions are so widely separated in their positions, the effect of the concentration is minimal. So the normal order of discharge is then followed. What I mean is, for example, you have fluoride. Fluoride is the first on the list of the anion. If you have fluoride and OH minus, fluoride ion and OH minus meeting themselves at the anode, their position is widely separated from each other. So even though fluoride is of higher concentration, but because its position from OH minus is widely separated, the ions are widely separated from each other, that will make the concentration effect to be very minimal. And in that case, the first factor, which is the position of the ion, is the one that will take dominance, that will now take charge, and the lower ion will then be discharged. That is The only that's the only kind of or alteration that could happen whenever you have high concentration. If the ions are widely separated, then the effect of that concentration will be very minimal. In that case, concentration will not be a determinant of which ion is to be discharged. Rather, it will now be the position of the ions, meaning that the lower ion is the one that will be discharged during the process of the electrolysis. Now, we want to look at the last part of the factor, which is the third factor. The third factor here is the nature of the electrode that is being used. The nature of the electrode that is being used. That's the third factor. Nature of the electrode. Now, when you talk about the nature of the electrode that is used, some electrodes like platinum and carbon are referred to as inert electrodes. Some electrodes like platinum and carbon, they are referred to as inert electrode. Why? Because they do not take part in the electrolytic reactions, even though they can be attacked sometimes by the products. They can be attacked sometimes by the products. So some electrodes influence the discharge of ions because of their affinity for it. Some electrodes, they influence the discharge of ions because of their affinity for it. So when you talk about influence, influence is in everywhere. When you now have a particular electrode that is used, the electrode has an influence. If one of the ions that is coming to the electrode is one of the ions that it has interest in. Take for example, if sodium ion should come to the cathode, and at that particular cathode, if sodium ion and hydrogen ion, they both come to the cathode, and what you use as your cathode and what you use as cathode is mercury. If you use mercury as cathode, now what you observe is that mercury has affinity for sodium. Mercury has affinity for sodium. Under normal condition, there is no condition that will have made sodium to be discharged. There is no condition that should have made sodium to be discharged. But because sodium has affinity, has delight, has desire for mercury, and because mercury has delight for sodium, has affinity for sodium, in that situation, mercury will take over. Mercury will attract sodium to itself. And rather than hydrogen being discharged, sodium will now be discharged. That is how the nature of the electrode used can affect or can influence the choice of the ions that is being discharged at a particular electrode. When a particular electrode is used and that electrode has an affinity for one of the ions, so regardless of the position of the ions, that will not count. What will now count is the delight, what the electrode has interest in. So the influence of the electrode will now take dominance. It will now dominate and attract whichever ions that is having an influence over or influence for. So that is how the nature of the electrode can affect the ions that will be discharged. I want to appreciate you for staying tuned to watching this video thus far. And I want to say once again, please subscribe. Subscribe to this channel. Please subscribe to this channel, as more other lessons will be coming up at this channel. Thank you for watching. Appreciate you. Until next time that we shall meet again. See you.